Hi everyone, welcome back to another video of our Ethereum series. And in this video, we'll learn more about blocks. So, why do we need blocks? We need blocks to ensure that all of the participants in the Ethereum network maintain a synchronized state of the EVM and agree on the precise history of the transactions. So this is not really a very novel concept anymore because I have covered it in my previous videos multiple times that blockchain is an open immutable store of transactions. You create a chain of multiple blocks and each block would have multiple transactions. These blocks are chained together, which makes it almost immutable in nature. And these blocks of the blockchain are hosted by a distributed network of nodes. So, why do we need blocks? We need blocks to ensure that all of the participants on the Ethereum network maintain a synchronized state of EVM and agree on the precise history of transactions. So, all of the transactions that have happened up until now on Ethereum network, all of the Ethereum nodes would contain data about it. The data would be in the form of a simple transaction, that is, A gave something to B, and all of these transactions are clubbed together in the form of blocks because they are very high in volume, and these blocks are then chained together using cryptography so that we have an open immutable ledger of transactions. Now, how are blocks used in Ethereum to preserve the transaction history? That is the sequence of transactions, like one transaction happened after another transaction, and so on. The blocks are strictly ordered, and the transactions within each block are strictly ordered as well. And each new block that is created, it contains a reference to its parent block. So that's how you get the entire sequence of transaction history right on the blockchain. To add a new block on the Ethereum network, a consensus mechanism called proof of stake is used. Earlier, Ethereum was using a proof of work consensus mechanism, but recently it migrated to POS. In POS or proof of stake, the validating nodes have to stake 32 ETH into a deposit contract as a collateral against bad behavior. If any validator tries to do anything fishy, the entire 32 ETH collateral is slashed to zero. And that's how it helps us in protecting the network against malicious actors. Now, in every slot, these slots are spaced 12 seconds apart. In every slot, a validator is randomly selected to be the block proposer. This block proposer bundles together the transactions. It then executes them and determine a new state of the EVM. Then they wrap all of this information into a block and pass it around to other validators. The other validators receive this data from the block proposer and they re-execute all of the transactions on their own system to ensure that they agree with the state of the EVM that the block proposer has arrived at. Assuming that the block is valid, they add it to their own database and the global state is updated. When other validators have verified and validated the transactions themselves, all of these validators arrive at a consensus to the new global state. If by any chance a validator hears about two conflicting blocks for the same slot, they use their fork choice algorithm to pick the one supported by the most stake ETH. So all of these validators have staked ETH as collateral, and minimum requirement is 32 ETH, but you can also stake a higher amount. So when a validator encounters two conflicting blocks, the block that is supported by the most stake ETH gets added to the network. And the simple rationale there is that since validators who have higher stakes are supporting a certain change in the state of EVM, which means they have a higher skin in the game because they have a lot to lose if anything wrong happens. Now, what's inside a block? When we talk about the contents of a block, these are the main contents of a block, and some of these might have a lot of data within them as well. So, the main contents of a block are slot, which means which slot the block belongs to, the proposer index, the ID of the validator proposing the block, the parent root, which is the hash of the preceding block, the last block's hash, the state root, the root hash of the global EVM state object, and a body. This is an object containing several other fields. So if you want a complete and exhaustive list of what all is there in a block, you can go to the developer docs, skip to the block section under foundational topics, and here you'll see a list of all of the things that are there in the block. So this is the main content list, and this is what all is there in the block body. And again, in the block body, each field can also contain a lot of data within it. Like in the block body, you have attestations, and then attestations will have a lot of data on its own. So do go through the complete list here once, and you don't need to understand all of it, and you don't need to memorize all of it. It would be good just to skim through it once so that you have a rough idea of what's all there in a block. Next, we have block time. Block time refers to the time separating these blocks. In Ethereum, the time is divided into 12-second units called slots. So each slot is supposed to have a new block, and ideally, a block should be added to the network in every 12 seconds. In each slot, a single validator is selected to propose a block. Assuming all of the validators are online and fully functional, there should be a block in every 12 seconds. But sometimes the validators are not there, they are offline when called to propose a block because of the network issues or some other kind of issues. So slots can also go empty. So in conclusion, we might not have a block in every 12 seconds on Ethereum. Now, each block on Ethereum has a target size of 15 million gas. This is variable. That means the block size can increase or decrease in accordance with the network demands. And the max cap on the block size is 30 million gas, which is two times of the target of 15 million gas. The total amount of gas expended by all of the transactions in a block must be less than the block gas limit. So if you have a target size of 15 million gas, then all of the transactions that are being included in that block combined should not spend more than 15 million gas. Again, it can change based on network demand, and the maximum that we can go is 30 million gas. This block size limit is important because it ensures that the blocks don't become unnecessarily large, and if they could be large in size, then less performant full nodes would gradually stop being able to keep up with the network due to space and speed requirements. So as you know, there is a lot of hardware requirement needed for running a validator node on any blockchain network. And if the block size is large, then these nodes who don't have enough hardware capacity, they won't be able to keep up with the network. And again, the network will start centralizing among a few validator nodes. So that's why this block size limit is important. So let's check out a block on Etherscan. Here we have a list of latest blocks. So we'll pick the latest one. And in this block, you can see all of the data about this block, like the number of transactions, timestamp, its status, and difficulty, the block reward, who received the fee for proposing this block, and again the gas used, the gas limit. The gas limit is 30 million right now. It was barely used, like 34%. And in more detail section, you can also see the hash of the parent block. Apart from that, you have some other things here like the consensus info and MEV info. So you can check all of this out for different blocks and just get a better idea of what's going on there in each block. So that was all about blocks on Ethereum, and in the next video we'll cover EVM.